Let's begin our discussion of organic structure. So organic chemistry, as you probably already know, is the study of carbon-containing compounds. So we're interested in understanding the structures of these compounds because to understand how they react, we have to know something about how they're put together. And so we're going to spend the first half of the course looking into those types of ideas. So let's start with just the basics of what does a Lewis structure show and how are we going to put one together? So what it shows, to address the first part of this question, what a Lewis structure shows is atoms and valence electrons. And you probably remember that the valence electrons are the ones that are contained in the outermost shell of an atom. Now, how do we construct one? So you probably learned in general chemistry a set of rules or guidelines to approach a problem like this. So let's review that in the context of this molecule here, which is called methane. Now, methane is an example of an organic compound that we call an alkane. An alkane is a special example or a special case of a hydrocarbon. So hydrocarbon is the broad category, alkane is a specific example, and a hydrocarbon is an organic molecule that only contains carbon and hydrogen. Now the ending of its name, ANE, tracks with the type of molecule it is. So we're going to be going through types of molecules, by the way, in a more systematic fashion a little bit later, but I wanted to start introducing you to some of these terms. So an alkane is a hydrocarbon. And specifically, it's a hydrocarbon that has only single bonds. So an alkane is a hydrocarbon with only single bonds. So to remind you how you would put together a Lewis structure, one thing you might do, looking at the formula, is try to figure out what will be the central element. Okay, now that's going to work well for smaller compounds. You're going to be able to do this. So we'll do this here because this is a fairly small compound. The central element typically is going to be the one that's closest to the middle of the periodic table. Which in this case is going to be carbon. So what you would do then would be to assess how many valence electrons are coming in with each of the elements present in your formula. So for your valence electrons, remember you go to the group number on the periodic table. And when you do that, you're going to find out that carbon has 4 valence electrons and that each of the hydrogen has 1 valence electron, and we have 4 of them. So we have a total contribution of 4 valence electrons from the hydrogen. That gives us a total of 8 valence electrons, and so that's going to have to show up. All 8 of those are going to have to show up in our structure. So we can start by drawing Lewis dot symbols. So putting the central element in the middle, and then arranging the Lewis dot symbols for the other atoms around the central element, like so. Let's move that guy over a little bit. So you would start, if you were building this from the ground up, you would start with the Lewis dot symbols. And then what you would do is pair unpaired electrons on adjacent atoms in order to make bonds and to fill octets. So that's what we're going to do next, is pair unpaired electrons on adjacent atoms to make bonds and to fill octets. Now, octets, let's go into that. So remember that an octet is a term that refers to 8 electrons. So most of the elements like to have 8 electrons around them. There are some exceptions to this, though. And the exceptions, there's actually quite a few exceptions, but the ones that we are going to run into are going to be things like hydrogen, which can only form 1 bond, boron, and aluminum. Notice that aluminum is right below boron on the periodic table, and so they're going to have some chemical similarity. Okay, so that's basically the idea. Put the dot symbols together, figure out what the central element is, and then start pairing unpaired electrons on adjacent atoms to make bonds and fill octets. So if we do that, it's basically just connecting dots like so, and now we have the structure of methane. Okay, now let's go back. We had 8 valence electrons that we need to account for in the structure. Do we have those? Well, each of these bonds in the methane structure that we've drawn, each of these lines represents 2 electrons. And so we have a total of 8 electrons. Now let's assess the octet. Around the carbon, we would count any of the electrons that are associated with that carbon or in bonds associated with that carbon. So to highlight the electrons around the carbon, we have 2, 4, 6, 8, and so the carbon has an octet. So that's a little review of how we would construct a Lewis structure given a molecular formula. So now pause the video and you try this for the next molecule, which is called formaldehyde. Okay, so if you pause the video, then you should have a structure. So let's work through this together. First of all, the name formaldehyde actually tells us what kind of organic molecule this is. What classification or what category does it fit into? It fits into a category that we call aldehydes. And again, we're going to learn these names in a systematic way a bit later in this packet of notes, but I'd like to start introducing you to these terms because we're going to be using them over and over again. So if we assess the formula CH2O, we have a carbon that has 4 valence electrons. So we get a contribution of 4 valence electrons from the carbon. We have 2 hydrogens, each with 1 valence electron, so that's a total of 2 from the hydrogens. And then oxygen, and the valence number of oxygen is, hopefully you said 6. So 6 electrons from the oxygen. So our total should have, or our total is 12 valence electrons, and our structure should show 12 valence electrons. Now, when you put this together, hopefully what you ended up with was a structure that looks more or less like this. So in this structure, unlike the previous one of methane that we worked on, we have 2 different kinds of electrons. We have electrons that are involved in bonds between atoms, and we also have electrons that are just hanging out on the oxygen. So those would be these guys here. You probably know them as lone pairs, and that's what they are. We're going to call them lone pairs throughout the course. We can also call them non-bonding electrons because they're not involved in bonds. So that's a term that we're also going to be using a lot throughout OChem. So lone pairs and unpaired electrons that are not involved in bonds are called non-bonding electrons, whereas any electrons that are in bonds are bonding electrons. Now, in organic chemistry, the structures get pretty complicated pretty quickly. So what we just reviewed in the context of drawing Lewis structures works very well for small molecules, and the conventions that you would be following when you're drawing more complicated molecules are exactly the same. However, as the molecules get larger, then you don't have a single central element. You'll have multiple centers. And so we're going to have to accommodate that. And the way to do that is to learn groupings of atoms that show up in all kinds of different molecules. So we're going to turn our attention to that a little bit later. For now, I'd like to show you a different way of drawing a Lewis structure that's called a skeletal formula. And this is what organic chemists typically use to show molecules. So let's talk about a set of guidelines that we would use for drawing compounds in this way. And then we're just going to start drawing some molecules, and see how the guidelines fall out, how we would apply these guidelines. So the first guideline is that every bend and every end represents a carbon atom, and I'll explain what that means in just a second. The second guideline, hydrogens are not drawn explicitly, so we're not going to draw bonds to hydrogens and show the H unless they're attached to what we call a heteroatom. A heteroatom in organic chemistry is an atom that's not carbon. So that would be things like oxygen, sulfur, halogen, and so on. Oxygen, sulfur, halogen, which we abbreviate as X. Nitrogen is another one you'll see a lot. Okay. So all of those guys and others. And then finally, the third guideline, we draw the structures generally to try to reflect the geometry around carbon atoms. Now, the geometry around a particular atom is a consequence of its hybridization. So the hybridization and the geometry go hand in hand with one another. Okay, so let's try this out, and let's start by drawing this molecule, butane. Now, butane is sort of a takeoff of methane. So first of all, it ends in ANE. And what that tells you is that this is most likely a member of the group of molecules called alkanes. So butane is an alkane. The beginning of its name, but, means 4 carbons. So what we're looking at, and the formula is given here, is a 4-carbon alkane. I'm going to draw it for you because, as it turns out, the 4 carbons in butane are arranged in a chain, we would call it. So just a row of carbons, like so. And all the remaining valences are filled by the hydrogens. Okay, so we're going to draw this in the skeletal format, or the skeletal formula format, but before we do that, I'd like to point out a couple of things within the structure. First of all, here's a grouping that you're going to see over and over and over and over again. So you have one here, and you've got one over here. These are CH3 groups, and a CH3 group is called a methyl group. So CH3 is called a methyl group. So 1 carbon, so remember methane is an alkane, meth means 1 carbon. So a methyl group is CH3. We also have, and I'll just circle one of them, CH2 units. A CH2 is called a methylene. So you can call these methyl groups and methylene groups, or just methyls and methylenes. To draw this in the skeletal formula, we would draw it like this. Okay, so now let's go back to the guidelines and see how we can apply them here. First of all, every bend in the structure is a carbon atom. So the bends are where I've highlighted the atoms with yellow. And every end is a carbon atom. So the ends of the chain on either side I've highlighted in blue. Second guideline tells us that hydrogens are not drawn explicitly unless they're attached to a heteroatom. So I'm going to number the carbons so that we have some points of reference. So 1, 2, 3, and 4. Just going to number arbitrarily from left to right. And let's take a look at the one that I've labeled as carbon 1. One bond is explicitly shown to that carbon, and that's the bond that links it to carbon 2. But we know that the valence number of carbon is 4, so carbon likes to form 4 bonds. That means that the remaining 3 bonds that are not shown must be to hydrogen. So at carbon 1, there are 3 hydrogens attached that we're not drawing in. At carbon 2, notice that there are 2 bonds explicitly shown. That must mean that there are 2 bonds that are not explicitly shown, which have to be to hydrogen. So there's 2 hydrogens on carbon 2, and then applying similar logic, we have 2 hydrogens on carbon 3 and 3 hydrogens on carbon 4. Now, this isn't really much of a surprise because the structure itself, the original Lewis structure of butane, is shown to the left. So we already know how many hydrogens are on each of these. But just so that we know how to translate a full-blown Lewis structure, which is what we're used to drawing, into this skeletal format. Let's try another one. Let's draw a molecule called acetone. Now acetone, its name ends in O-N-E, which places it, or suggests that its placement is in a group of molecules that are called ketones. So ketones that's another class of organic molecules. Now, oftentimes when you're drawing these Lewis structures in the beginning of organic chemistry, they give you the formula more or less in the order in which the atoms are bonded. So what this is showing us in this formula is that you have two CH3 groups, so you have two methyl groups. They're both attached to this carbon that I've just highlighted in the formula, which is attached to this oxygen. Now, when you sort all of this out and you take into account the fact that this is a ketone, that gives you a lot of information about how to draw the Lewis structure for this without having to go through the trial and error that you may have had to go through on the previous page with formaldehyde. So knowing that something is a ketone, for example, or an alkane or an aldehyde, automatically is going to give you a head start on drawing the structure for it. When we draw the structure for acetone, it's going to look like this. So we have two CH3 groups, and those are both attached to the carbon that's doubly bonded to this oxygen. This brings up a new group of interest, which is C double bond O, and this is called a carbonyl group. So C double bond O is a carbonyl group. So what we've just drawn is the full Lewis structure for acetone. Now there's different ways that we can abbreviate this. We don't have to go right to the skeletal format. So let me show you another couple of ways that you could draw this. So you could just abbreviate the methyl groups as CH3. And over here on the left, you might want to draw it a little bit backwards. You could think of it H3C, and that's just to suggest that there's a carbon-carbon bond right there. Now you could also draw it like so. Now that's not very different. What's different about it is the way you're showing this carbon-carbon bond that I've highlighted. We know that that carbon, the one that's doubly bonded to the oxygen, it already has three other bonds. It's got the 2 to the oxygen, it's got 1 to the methyl group on the other side, on the right side of the structure, and so it can't be bonded to all three of those hydrogens in the methyl group on the left right here. So it's implied, we understand that it's actually bonding to the carbon and that those three hydrogens are coming off of that carbon on the far left. I point this out because you'll see this drawn in both of these ways, and both of them are totally correct. Now, let's draw this as a skeletal formula. So it's a 3-carbon chain. So we're going to draw that like this. It's the central carbon, the middle one, that's doubly bonded to the oxygen. And so we would draw that like so. Now at this stage of the game, we always want to include the lone pairs on everything. Notice though that we don't have to include the hydrogens on the methyl groups. So it's assumed, because no charges are shown, that each of these carbon atoms have full valences. So they have 4 bonds. With each of them, only one of the bonds is shown. That means the remaining 3 bonds that are not shown explicitly must be to hydrogens. So there's 3 hydrogens on this carbon and 3 hydrogens on this carbon. Let's try another one. This one is called acetic acid, and you've probably run across acetic acid more than once and in more than one context. Okay, so first of all, acetic acid is what's called a carboxylic acid. And all carboxylic acids have the same grouping of elements that's found in the formula, the part of the formula that I just highlighted. So COOH, or we could have written this CO2H. That means exactly the same thing. So what you'll learn in organic chemistry is that, unfortunately, there's a lot of different ways of expressing the same information. So you have to become comfortable accommodating that. You might see things written in more than one way. Okay, so what this is showing us is that there's a methyl group attached to a carboxylic acid. We would call it a functional group. So this COOH would be the functional group. So COOH, in the context of a carboxylic acid, is this piece, and then we have a methyl group attached to that, like so. So here's our COOH piece. And so what we can do with this now to draw it as a skeletal formula is the following. So there's 2 carbons in the molecule. Here they are. And here they are in the skeletal formula. The carbon that's doubly bonded to the oxygen also has a single bond to another oxygen. Again, we want to include all those lone pairs. And then there's a hydrogen that we have to deal with. Now remember up above, you can kind of see it on the top of the screen. Oops, no, that's not what I'm looking at. Up above it says, let's just sneak up there, hydrogens are not drawn explicitly unless they are attached to a heteroatom. Well, in this structure, we do have a hydrogen that's attached to a heteroatom. And so we're going to draw a bond and stick that guy on there as well. Now, another thing that you can do when you have a hydrogen that's attached to a heteroatom, you don't necessarily have to draw the bond. If you're just wanting to show the structure, you don't really need to draw the bond in all cases between the heteroatom and the hydrogen. So on the right, I've drawn an alternate way of drawing acetic acid, which is also correct. Let's do one more of these. 2-butyne. Okay, now we already know what but means. But is a prefix that means 4 carbons in the molecule. YNE is a new suffix that tells us that this molecule is something called an alkyne. An alkyne is a molecule that contains a carbon-carbon triple bond, as we'll see a little bit later. So 2-butyne is going to look like this. Here's the carbon-carbon triple bond. And so the carbon-carbon triple bond is flanked on either side by a methyl group. We have 4 carbons in a chain, so that would be, that gives rise to the prefix but, 4 carbons. And so if we want to draw this one in the skeletal formula, it's going to look a little bit different than what we've been doing so far. It's going to look like this. Okay, so let's see why. Now, one of the things we're going to be talking about a little bit later in the course is the hybridization of particular atoms. So the hybridization of the carbons involved in the triple bond, you might remember, is sp. As such, each of these carbons has a 180-degree bond angle. So it's in the middle of a 180-degree bond angle, which means that the structure in the vicinity of that triple bond is linear. So we need to reflect that geometry in the structure that we draw. So this molecule has a linear geometry. All right, now let's think again about the guidelines. The first guideline said that every end and every bend is a carbon atom. This is an exception to that because we don't always have bends because of the geometries around sp hybrid carbons. So there's not going to be a bend around those carbons. So looking at the skeletal structure, I'm going to highlight the 4 carbons. So we have 1. The junction between the single bond and the triple bond is the 2nd carbon. Then on the other side of the triple bond is the 3rd carbon. And finally, here's the 4th carbon. Okay, let's look at one more idea, and that is this idea of constitutional or structural isomers. Sometimes you can run into this when you're trying to put together some Lewis structures. So first of all, let's get onto the same page in terms of the definition of isomers. So if you have a pair of molecules that are isomers, or a set of molecules and they're related to one another as isomers, what that means is that they all share the same molecular formula. Isomers are what we would call constitutional, or you can call these structural isomers, if they have the same molecular formula. But what we would call a different connectivity. So same molecular formula, different connectivity. That defines constitutional isomers. But now we need to define what we mean by connectivity. That's just the order in which the atoms are bonded. So let's look at some examples of this. First example, let's look at this formula. C2H6O. As it turns out, there's 2 reasonable Lewis structures that you can draw for this formula. Here's one of them. And here's the other. And remember, you want to include the lone pairs on all the atoms that have them. And I'm going to just clean up my structure a little bit, like so. Okay, we want things to look nice, and we don't want to have any problems interpreting structures. So these are both reasonable Lewis structures for the formula C2H6O. But notice that the order in which the atoms are bonded is different in each case. So in the left case, the order of bonding is COC, but in the right case, it's CCO. So these are entirely different molecules. They have different physical properties. They have different names, but they have the same molecular formula. So they are constitutional isomers of one another. Let's look at another one, C5H12. Okay, so here's a molecule, a structure, a skeletal formula that has the formula C5H12. This has 5 carbon atoms in it, in a chain. We call this pentane. So pent, meaning 5 carbons, ane, this is an alkane. Okay, so let's say that we mentally pull off one of the methyl groups on the ends of the molecule, and we're going to tack it on to one of the central carbons, or not central carbons, but interior carbons, like so. Okay, that has the same formula, C5H12. We can do this again and come up with this structure, also C5H12. So all of these have the same formula, but the atoms are bonded in a different order. So these are all constitutional isomers. And then one final example. Here's an organic molecule that actually has a bromine attached to it. So this would be called an alkyl bromide or an alkyl halide. We'll get into the details of that later on. So notice that in this case, with these two structures, the carbon skeletons are the same. So the carbons are all bonded in the same order, but it's the position where the bromine is attached that's different. So these are also constitutional isomers of one another. So with these ideas in hand, reviewing some things about Lewis structures, looking at some new terminology, what we need is some information about what are the repeating patterns that we're going to see in a lot of organic molecules so that we don't have to reinvent the wheel and go back to the drawing board every single time we draw a Lewis structure. So once we know these patterns, we're going to be able to assemble Lewis structures very, very rapidly. So that's what we're going to be doing as we go forward.